we saw that the muscle mitochondria, actually a lot of the training-induced improvements that you would expect, and we saw in the placebo group, were blunted in the metformin group. And I think that's the primary finding of the study.
humanOS. Learn, master, achieve.
Hello, everybody. I'd like to welcome Ben Miller to humanOS Radio. Ben is the principal investigator in the Aging and Metabolism Research Program at the Oklahoma Medical Research Foundation. His lab studies the interaction of mitochondrial energetics, protein turnover, and stress resistance with the overarching goal of slowing the aging process and extending health span. We've addressed aspects of the aging process many times before on the show. People are living longer than ever before, but as we get older, we become more susceptible to chronic degenerative disease, which gradually robs us of our independence and reduces the quality of our lives. So we may live a long life, but much of those years are spent relatively unhealthy. So we don't merely want to live longer without good health. We want to increase our health span as well. This has given rise to interest in the pharmaceutical industry and with pharmaceutical drugs that could target the aging process itself, not just chronic disease. One potential candidate is the anti-hyperglycemic drug Metformin. Metformin has been around for a long time. It was discovered in 1922 and first introduced as a medication in Europe in 1957. It is now the most widely prescribed medication to treat type 2 diabetes in the world, and the fourth most prescribed medication in the United States, with more than 81 million total prescriptions in 2016. Reviews of the literature have shown that people with diabetes who take metformin are at reduced risk for cardiovascular disease, cancer, and all-cause mortality. It appears to extend lifespan and augment health independent of its effects on diabetes. Sounds pretty good, right? So does this mean that everyone should start taking it? Maybe not. It has been shown for some time that metformin may actually interfere with the health benefits associated with aerobic exercise, particularly in insulin sensitivity and cardiorespiratory fitness. A recent study from Ben and his team found this to be the case and also sheds light on some of the reasons why this antagonism occurs. So I am delighted that he is here with me today. Ben, welcome to humanOS Radio.
Thank you. I very much appreciate the invite.
So before we dive into the study itself, let's talk about your background. How did you become interested in biogerontology?
Actually, I was not trained in that area. I was trained in metabolism and became an expert in the use of stable isotopes during my Ph.D. I went to do a postdoc in Copenhagen, Denmark, at a famous muscle research center there. And during that time, I actually started to become interested in the aging process and the loss of muscle mass with time. As I moved forward in my career and then subsequently moved to a new institute, I really started to focus in on mitochondria and aspects of protein turnover and the making of mitochondria as it pertains to maintaining muscle mass with age. During that time, I found aging to be a really fascinating question. And I suppose as I've gone further, I've gotten more and more into the basic biology of aging. So even though muscle continues to be my primary tissue of interest, all these other tissues and what is basically driving the aging process has become more and more a part of the research process. So we tend to look at a variety of organs, not just muscle, with a little bit of an increasing focus on the brain, although we're still rather novice in that area. It's really interesting to me what fundamentally is going wrong to cause this deterioration over time and how we might slow that process.
Most people know that aerobic exercise and cardiorespiratory fitness prevent chronic disease, but they might not know much about the underlying chemistry. Talk about how activation of AMPK, the enzyme, contributes to the health benefits associated with exercise training.
So AMPK is basically this energy sensor of the cell. It detects when your ratios of ADP to ATP change and then put in motion processes to correct this energetic stress that you have at a particular time. With exercise, obviously with aerobic exercise, especially, you have this activation of AMPK during the exercise bout. The temporal response actually is not completely well defined as far as when you have activation, when you restore that to normal homeostatic state around the bout of exercise. But it's pretty safe to say that the aerobic exercise itself stimulates AMPK. Once you stimulate AMPK, you have a whole host of downstream effectors, as you can imagine, to correct this energetic deficit, which winds up changing the metabolic program at that period of time and changes what the cell does to deal with energetic constraints. Your cell can't do everything at once. All these basic processes cost energy. So if you think about making things like protein, that's energetically costly. In reality, it's one of the most energetically costly things your cell does. And if you think about the pumps and you think about everything else that's going on in the cell, while at the same time, say in the muscle, having to produce energy to activate this cross-bridge cycling that allows you to perform contractions. So it's a delicate balance, it's a complicated balance, and it's something that's not completely figured out yet.
And what does the activation of AMPK lead to in terms of some of the cellular responses that we see?
Acutely, one thing for sure, it will go through the mTOR pathway, which is downstream of it, and turn off the making of protein. So like I said, making proteins is energetically costly. So that is something you might not need to do while you're exercising, and that process gets shut down. And so it makes those decisions to be able to do what you need to do at that period of time. Again, I'll say that the temporal response of this is very complicated because we know that something like aerobic exercise will then lead to adaptations to better respond to that. This is a stress resistance, or you impose a stress on a cell and then later on it makes adjustments to be able to respond to that stress better in the future. So as soon as acutely that AMPK activation may be down, but if you think about the fact that the cell then needs to adapt to that stress, you will reverse that when you have energy available again to be able to make the adjustments that you need to adjust to that stress.
So we know that exercise will elicit that. Metformin appears to activate AMPK as well. How does it work? How is metformin similar to and different from exercise-induced AMPK increases?
Believe it or not, how metformin works is really one of the million-dollar questions right now. So it's not exactly known what the mechanism of metformin is. We do have a sense, although the data are not conclusive, that it might be a complex 1 inhibitor of the complex 1 of the electron transport chain in mitochondria. So if it's a complex 1 inhibitor, that might create an energetic stress that activates AMPK. So we know that metformin is an AMPK activator, although we don't know exactly how it is an AMPK activator.
Let's do a primer on the electron transport chain. What is the purpose of this electron transport chain? Why is it activated? What is its function?
So this is the way that your body produces energy, or your cells produce energy. They take substrates in the form of glucose and fatty acid, and those substrates are made into these reducing equivalents that are then used in a series of redox equations through the electron transport chain. So you go from a gradual increasing state of oxidation and reduction in order to harness that energy to pump hydrogens across the membrane. And then at the end of that chain, you let that hydrogen come back through a complex in order to couple the formation of ADP to an inorganic phosphate to make ATP. If you think about it, there's two analogies here. The engine of a car that takes gasoline, combusts it to make it into usable energy. That's sort of what your mitochondria are doing, using your nutrients as the fuel source. And you can also think about it as pumping these hydrogens and building up a potential energy like you would in a dam, and then releasing that dam and coupling the energy to the formation of usable energy for the cell.
Even though we're not exactly sure how it works, we might be working at complex 1 of the electron transport chain to make, interestingly, that process less efficient. It's not trying to help the electron transport chain work better. It's actually interfering with it, correct?
Yeah, it is interfering with it a bit. And it's thought that that occurs, although there are data that shows that it may be the case and it may not be the case. And that's one of the parts that haven't completely been worked out yet. And if it does inhibit that process, then yes, that is energetic stress, saying the mitochondria are not working as well as they should be, or not producing the energy in a way they should be, and that might trigger adaptations. Another thing to keep in mind is that metformin is transported very well into the liver, and some of the primary effects as a glucose-lowering drug is thought to be mediated through the liver, and to control or inhibit hepatic glucose output to control the level of glucose in the blood. So muscle, where we looked in this particular project, is not thought to be a primary site of metformin action, although there are many of these other tissues besides the liver that will take up metformin and have effects there as well.
We see that exercise is doing a lot of the same things as metformin. So you might think that combining metformin and exercise might have additive or even synergistic effects, but research has failed to show this. What has previous research shown when metformin and exercise were used together?
Most of the previous research that led to this was really focused on the cardiorespiratory effects of a combination of metformin and exercise, aerobic exercise. The major studies done prior to ours were able to show that metformin sometimes blunts the increase in VO2 max, your measure of cardiorespiratory fitness, when taken in combination with the aerobic exercise training. That was shown both acutely and over exercise training program.
Right, that's interesting. And cardiorespiratory fitness is not just something that athletes care about, but it is something that correlates very strongly with longevity and health into the future. So something that would interfere with that would be problematic. That's what we had seen previously, that there was this interference with metformin on cardiorespiratory fitness. What was your hypothesis and what was the protocol for this research?
What we wanted to do to extend the previous findings is to look into the skeletal muscle and to look into the mitochondria of the skeletal muscle to see if some of this blunting of these positive effects of aerobic exercise training were happening at the muscle. So we enrolled a number of subjects who were at risk for type 2 diabetes. So nobody in our study had type 2 diabetes, but they had at least one risk factor. For many of our subjects, that was just a family history. Once they were enrolled, we underwent a series of tests, including measuring cardiorespiratory fitness and taking a muscle biopsy from which we took muscle fibers and looked at the function of the mitochondria in a specialized instrument to look at mitochondrial function. We also did a measure of insulin sensitivity. They then underwent 12 weeks of exercise training program. They were randomized into a placebo or metformin group. They were able to self-select mostly their exercise training, whether that be an elliptical, biking, or running. And we gradually progressed them through a 12-week training program that are pretty standard exercise training programs. Unintentionally, we got a variety of cardiorespiratory fitness of the people enrolling the subjects. So we had subjects that were somewhat active, and we had subjects that were very close to being diabetic. This wound up being a strength later in the study, although at the time we didn't realize that. So we enrolled men and women. On average, they were about 62 to 63 years old, so they were a little bit older. And at the end of the study, we repeated those baseline measurements. And what we saw that was quite striking is that we reproduced that blunting of cardiorespiratory improvement with exercise training that other studies had shown before. And we saw that the muscle mitochondria, actually a lot of the training-induced improvements that you would expect, and we saw in the placebo group, were blunted in the metformin group. And I think that's the primary finding of the study. What we also saw, though, was that the improvements in insulin sensitivity were also blunted. Not only were they blunted, but there was a huge variability in responsiveness. So although the subjects that were on placebo, by and large, all of them improved with the exercise training program as far as insulin sensitivity, it was almost about 50-50 from the subjects that were on metformin that improved or did not improve.
That's interesting. Were you able to do a subgroup analysis of the responders and the non-responders to metformin with insulin sensitivity?
So in the paper, we did not. But going back and looking at the data, we started to look at what were the characteristics of those subjects that responded well and did not respond well. And those findings have led to a future study, which we're going to start in the next 2 months or so, that directly tests some of these factors that we think might impact whether people are responders or non-responders to the metformin treatment.
When was the metformin taken relative to when the exercise occurred? Was it taken at the same time every day? And what was the dose?
We used a clinical dose of metformin, which is about 1,500 milligrams to 2,000 milligrams per day. We were targeting 2,000 milligrams, but one of the common side effects of metformin is gastric distress. So in some subjects, we had to back it down to 1,500 milligrams per day. The dose is split between the morning and the evening, and that was the same every day. But we did allow the subjects to exercise based on when it was convenient for them.
So that exercise was not standardized at a certain time. This could have happened anytime during the day. The participants chose when to do it.
Right, but chances are by the schedule that most of them would have exercised between the morning and the evening dose.
Do you take metformin on an empty stomach? How is it usually dosed?
They actually encourage people not to take it on an empty stomach since it does have some gastric distress with it.
Okay. There wasn't really variability in terms of the cardiorespiratory response. Metformin inhibited exercise-induced improvements in cardiorespiratory fitness. But in terms of insulin sensitivity, that's where you see this dichotomous response. Some people had improved insulin sensitivity and some people did not. For those who had improved insulin sensitivity, how comparable was that improvement to those in the placebo group?
So if you look at the extremes of the placebo and the metformin, you will see subjects that had equal improvements in insulin sensitivity. You do not see the spread and the variability of responsiveness in the placebo group that you see in the metformin group.
Were you able to assess skeletal muscle mitochondrial respiration? And how did you do that? And what did you find?
Yeah, so that was one of our primary outcomes. To do these procedures, you use a muscle biopsy, you isolate out some of the muscle fibers from that muscle biopsy, and basically you use detergent to poke some holes into the muscle bundle. And what that allows for is for you to then introduce substrates and inhibitors into this isolated prep. So this prep goes into an instrument that's designed to measure oxygen consumption. These are obviously very sensitive instruments. You have a known amount of oxygen in this chamber, and as that oxygen declines, you can measure a rate of respiration. So the rate at which the mitochondria in these muscle fibers are using oxygen. And then you go through a series of steps where you can titrate in different doses of, say, I want to look at just the function of complex 1 or complex 2. You can control that by adding substrates and inhibitors to the chamber. So you can sort of tease out where you might have positive or negative effects in the mitochondria. Again, the advantages of the method that we used is you leave the mitochondria intact in this muscle prep. So they're keeping their shape. They're not being isolated out. There's advantages and disadvantages to both approaches of isolating mitochondria or leaving them intact. But for our purposes, we preferred to keep them intact.
You're able to put into this medium a variety of different substrates. Depending on the type of the substrate used, you can assess different aspects of mitochondrial function. Is that correct?
Yes, that's correct.
Tell the audience how you're then assessing what part of the mitochondrial electron transport chain is activated and challenged.
I mentioned the fact that you have these redox equations in the mitochondria, and where that energy comes from is passing an electron. So if you pass electrons through the complexes, you can assess that by itself, or you can assess the mitochondria's ability then to couple that to ATP production. Another thing is that when you do these experiments, you typically provide all these energy substrates and oxygen and everything else in what's considered saturating doses. You don't want any of those things to be limited so that you look at the maximum function of the mitochondria. What we did in this experiment that we think is very important and we've adapted in the lab is that we also do experiments that the mitochondria aren't running at full max. We titrate in ADP to make ATP, but we titrate that in at submax doses so that we can look at how well the mitochondria are working under conditions that are more like what it would see in the muscle. And I would say under those conditions is where we saw the most striking effects. We saw an increase in the ability to consume oxygen at a given ADP concentration as we went through this gradually increasing concentrations of ADP. We saw a very nice improvement in the placebo group post-exercise, as we would expect. In the metformin-treated group, that's where we saw a complete blunting of the positive effect that we saw with the placebo group.
So these were samples that were taken out of a leg muscle in the participants, and you had before and after samples so you could see the difference over time?
Correct. We do the measurements as soon as we get the muscle because it has to be done on fresh tissue. We compare their responses after the training bout to the responses that we got before the training program, I should say.
As you'd expect with exercise training, the process by which these mitochondria make energy becomes enhanced. An increase in the number of mitochondria and efficiency per mitochondria.
These experiments, we're testing the combined effect of both mitochondrial content and mitochondrial function. So how well the mitochondria work and whether there's an increase in the mitochondria total. You can tease apart those two factors. We did not do that so much in this study, but it is something that's possible to do.
It would have been interesting to see a group taking metformin without exercise. If you take a group of non-exercise people and you give them metformin without exercise, is there actually an improvement in the respiratory capacity of the mitochondria? That's what this is coming down to for me. There might be a benefit of taking metformin in a sedentary population. It's not quite as good as exercise, but it's better than being sedentary.
Right. Something that we're moving towards now is directly testing that kind of question, because you're left with two unknowns in this study. So is this a blunting that we only see in the face of an exercise training program, or is it have to do with the population that you're looking at?
You also measured a few other things, telomere length. You want to tell us quickly about what you saw there?
The telomere length was interesting, although maybe not directly related to metformin. Telomeres, as you know, are these markers that decrease in length over time and that could or could not be tied to the aging process. They tend to be a sensitive marker of disease if you're looking at them the right way. And in our study, although we did not see an effect of metformin, what was interesting is that telomere length was increased post-exercise training. And to say that a telomere increases in length is actually kind of an interesting observation. And it turns out this has been repeated in other studies. I shouldn't say repeated because we repeated what others have found, that exercise can increase the lengths of telomeres. And we generally think of telomeres as just shortening and maybe blunting the speed at which they're shortening. But to actually have an increase is something that's interesting and maybe I don't have a direct answer for right now.
Was there any difference between metformin and exercise?
No, so that was just the effect of exercise is all we saw in that outcome. And it was equal between the two.
What are some studies that you're looking to do next in order to advance our understanding further?
One thing I want to comment on is that this study was with aerobic exercise training. There's a study that recently finished up called the Masters trial, where they did metformin and resistance training. So metformin is thought to have some anti-inflammatory effects. And the thinking these researchers had was that if you blunt some of this inflammation with metformin in older individuals, you'd have a greater response to the strength training. So for some reason in that study as well, metformin blunted the positive effects of strength training. So those data are not published yet. I've talked to the investigator, the PI on that project several times, and because we've saw similar things. And so it's interesting that it was the same with aerobic and strength training. Where does this lead us next? It's exactly is to answer some of the questions you brought up. So what is happening when you don't have aerobic exercise involved in the process? So your normal everyday population that may not be exercising or physically active, that's a question of interest to us. And then within that population, who are the people that do well with this treatment and who are those that might not do as well? And the reason that's important is because the concept of health span that we've been focused on is the idea of prolonging the period spent free of disease. So if we want to have a treatment that prolongs health span, that by definition has to occur before the onset of disease. That means you would be providing a pill to someone that doesn't have disease yet. So the rationale for using metformin or the positive data that has been generated for metformin has mostly been done in people with type 2 diabetes. And it has very positive effects in people with type 2 diabetes. But if you look at something like the diabetes prevention program that looks at the progression to diabetes, so these were people that were pre-diabetic and not sick yet, the subjects that were the most healthy in that study were the ones that had the least benefit. We need to start understanding better in the people that are already healthy, does this have a benefit at all? And it's one thing to say that it doesn't have a benefit, but it's another thing to say that it might have detrimental effects. And I think that's what we want to understand more.
What is the half-life of metformin? And is it possible that timing could be a factor in its effect? So you could imagine taking metformin just on sedentary days or in the evening to augment the benefits associated with the fasting period. That is not a very clean idea for people. It's best for people to just say, take this at the same time every single day versus having to then judge how physically active you are. But I wonder if that is an area where an informed person could be managing this around what else they're doing in their life.
The half-life on metformin is very short, and I should be able to give you the exact hours, but I can't. But it is short-acting. And so that does leave open that possibility. But I'll tell you that in our study, we took our muscle biopsies 36 hours after the last dose of metformin and 48 hours after the last bout of exercise. And we did that for a very good reason. We did that because we didn't want to look at the acute effect of a dose of metformin. So obviously there are some long-term impacts of taking metformin that extend beyond just that acute period in which the medication is in the system.
Could dose be a factor? Is it possible that healthy people seeking the anti-aging effects could use a lower dose, thus minimizing the drawbacks, but still getting some of the benefit? If you don't have diabetes, could you take a sub-diabetic dose and get a different effect?
I think that's a really good question and something that we've considered when we were thinking about what direction to go next with this research. The dosing and taking lower doses of metformin is the direction we haven't gone, but I definitely think that's a question that remains to be answered yet. Could you have positive benefits in those that are not diabetic by lowering the dose and having these subacute effects that are beneficial over time?
We know that lifestyle modification, so doing 150 minutes moderate intensity exercise per week, prevents the progression from prediabetes to type 2 diabetes by 58%, where metformin has shown to prevent that progression by 31%. So both are eliciting a positive effect here. I wonder if we could identify a level if you say, well, I'm not entirely sedentary. I'm not necessarily training hard, but I do walk every week and I'm doing some degree of physical activity. And then you compare that with people who are actually able to maintain the national guidelines for exercise recommendations. Can we figure out an algorithm where if you assess somebody's physical activity level, then you could say, okay, this is a person where metformin will be additive. And if you are currently maintaining a level above this, then you're inducing the effects of metformin even more so. So stick on your regimen until you can't do that any longer.
That's an interesting direction to go and one that I hope we would get to at some point. Right now, when we think about, okay, should we prescribe metformin for slowed aging? There's not that sort of nuance in it right now. And all it is that, okay, well, we need to put people on metformin and see if it slows the aging process. And I'm all for finding the right treatment to slow the aging process. A lot of research with exercise training, and I know exercise training works, and I'm a huge advocate for it primarily, but the reality is that we can't get everybody to exercise, and we do have to find some alternative approaches to it to slow this aging process. And that might come in pill form, and it may be metformin, but I don't think we're at a point right now where we understand enough that we can say that, yes, this is the slowed aging treatment that we should use first.
It sounds like metformin's effects on the complex 1 in the electron transport chain of the mitochondria, it could have an effect there, although it might not. Is that exclusive to metformin, or do we know other molecules that also will interfere with aspects of the electron transport chain, making them less efficient and therefore possibly inducing being an exercise mimetic?
I hesitate to say exercise mimetic for anything, just because we know the wide range of effects that exercise has besides just on the electron transport chain. It sounds nice. I just don't think it's possible to capture that in a pill. But there are drugs that have effects at the mitochondria. You know, there's a whole series of drugs that are targeted antioxidants to the mitochondria, or they upregulate systems in the mitochondria to defend itself. And there's a whole series of those types of drugs out there. I think what is common that we see in some of these drugs is you're activating pathways that are stress responsive. Mm-hmm. You know that low dose stress is a very positive thing because the cell is then challenged and it has to adapt to that challenge. Mm-hmm. And inactive and leading a sedentary lifestyle is sort of the absence of challenge until things become too dysregulated. We know that's how a lot of the phytochemicals and botanicals work. These are very low dose stresses to the cell. Mm-hmm. And as far as we know, that's one theory of how metformin is working, is it's stimulating this low dose stress. And then there's a lot of stuff with the fasting period and how long to fast and whether that triggers some of these stress responsiveness in the same way. I think those are all really interesting areas. There will probably be some common themes that emerge with these different treatments.
It's nice when that happens because you can see that there might be multiple ways to get at the core effect that we're looking to do, whether it's through plant phytochemicals, fasting, exercise, and other sort of low-dose hormetic stimulations. We see the induction of these survival pathways that support health. If we can do that through lifestyle, that's probably better because, like you said, an exercise mimetic is an oversell. We know that exercise is doing so much to the body. The entire effect of exercise is not happening just at the electron transport chain. But for the vast majority of people who are increasingly so are not living that healthy lifestyle, if there are these other pharmaceutical agents that have a lot of data behind them that show it does reduce the progression from prediabetes to diabetes, reduces the risk for cancers and cardiovascular disease. Like you, I'm up for it as well. Our emphasis should always be on, can we do this by the way we live first? And then when we can't, then how do we do better?
Yeah, exactly.
Are there other compounds that you're looking at in your lab?
Yes, we've used some of the common, what you would call hot area of slowed aging treatments. We've worked with rapamycin quite a bit, obviously not humans for rapamycin. We've worked with compounds that activate NRF2, which is a transcription factor, which is known as the master regulator of the antioxidant response in the body. Those have been our primary. We're beginning work with 17-alpha estradiol, which is a non-feminizing estrogen, but that seems to work only in males and not in females. So we've had our hands on a lot of these different treatments and caloric restriction. A lot of these are teaching us about the basic biology of aging. The NRF2 activators aside, I don't know if any of these are practical for human treatment, but these are things that we can learn from to potentially understand the basic biology of aging so that we can then design more reasonable alternatives to some of these things that we know but might not be good for humans.
And so interested in the National Institute of Aging's program, looking at the various compounds that have an impact. Rapamycin was top, that had the greatest effect. Acarbose was second, and then things like 17-alpha estradiol, methylene blue, a couple of other compounds seem to be quite interesting too. Do you know the mechanism for the 17-alpha estradiol?
I do. So I'm working with someone that's probably put more work into this compound than anybody else. And his name's Mike Stout. He's doing some great research. And a lot of his data are indicating that these compounds, or the 17-alpha estradiol, is having effect in the brain that regulates appetite pathways. So it's probably having a metabolic effect.
Are the compounds that you're looking at as NRF2 activators, are those natural compounds or are those synthetic?
Yeah, so we work with a company that has designed the compounds based on synergism between multiple compounds that work well together to activate NRF2. We did have one in the NIA program that you talked about, and that extended lifespan, median lifespan in male mice, but not female mice. But we have a second generation that's in testing right now.
Might that be commercialized in the future, or is this just a purely research endeavor?
The one that's in testing right now is actually available commercially.
It's such an interesting subject. And I can't tell you how many questions, text messages I've gotten from colleagues and friends that are saying, hey, where do I get this stuff? And I'm looking at these mid-50-year-old men who are very fit, who exercise regularly, who take care of themselves. And what I appreciate about it is that they care very much to implement whatever's cutting edge so that they can preserve their health span as long as possible. And I've warned them against adopting metformin as a strategy to employ at the moment because they're not the population where this is shown to be beneficial.
Right. And if you consider exercise as a drug as well, and we know that there's drug-drug interactions, I think that's one worth considering then with these other treatments.
Well, thank you so much for your time and coming on to join me on humanOS Radio today.
I appreciate it, and I appreciate you highlighting the topic.
Thanks for listening, and come visit us soon at humanOS.me.